Hello everyone. Today in this class we will be seeing the definition of the Riemann sum. So let f is mapping from closed interval a comma a to R be a bounded function, and we have defined a partition P that is equals to a, that is equals to x0 x1 so on up to xn equals to b, that is let it be a partition of closed interval ab. Now rth subinterval is defined, that is IR is equals to XR minus 1 comma XR. And now we will be talking about the length of the subinterval. So the length is defined as delta R. What is delta R? You already know it is B minus A. And as we are talking about the sum of the partition sum, we will be having a set that is epsilon 1, epsilon 2 and so on, epsilon n. That is subset or equals to the open interval a comma b. Okay, this is subset or equals to the open interval a comma b. Now in the next line we have to define this xr minus 1. So this epsilon 1r will be lying in epsilon. This is epsilon 1 1, epsilon 1 2 and so on, epsilon 1 n. So xr minus 1 is less than or equals to epsilon 1r is less than or equals to xr. Then the sum is defined as f of epsilon 1 into delta r plus f of epsilon 2 into delta r, that is delta 1. We are talking about the first length of the first one and length of the second one, so you'll be having delta 2 and plus so on f of epsilon n, that is 1 2 1 1 and 1 n. See, based on this interval you have to define the sum into delta n. So this will be equals to, what is that sum? I'm just putting everything in the summation. So summation r is equals to 1 to n f of epsilon 1 r into delta r. So this is called the sum of Riemann sum of f on closed interval a comma b. So now the very important is a note point. So for the note point, in the note point they will be defining, like if there is some function which is mapping from a comma b to the Riemann integral, then we can tell that whatever integral, that is integral a to b f of x dx, is clearly equals to the limit norm p. I hope you all know the definition of norm p. We have did in the earlier classes. If you did not see the video, please go to the earlier class and see. So limit norm p tends to 0, that is summation r is equals to 1 to n f of epsilon r, that is 1 r into delta r. So this is just a note point. Remember, whenever the integral is whenever you have an integral of the function, that will be equals to the limit where norm tends to 0, and you'll have that summation. Now coming to the very important theorem, that is, I don't remember the theorem number properly. Just take down the note. Theorem is fundamental, very important theorem. You may expect this in your semester exam. So fundamental theorem of integral calculus. Fundamental theorem of integral calculus. So let us quickly look into the statement of this. The statement says, if there is a function f which belongs to R, that is Riemann integral of a comma b, and they have defined a phi of x. This is a primitive. This phi of x is primitive. This is primitive or anti-derivative. I hope you know the what is derivative. Then you have to put anti for that. So it is anti-derivative, that you have to take the inverse. So of f of x. Then they are asking us to prove integral a to b f of x dx is equals to phi of b minus phi of a. So please do remember that one. What is primitive? Primitive is phi of x is equals to integral f of x dx. Or you can also write that as or phi of x is equals to f of x dx for all x belongs to closed interval a comma b. So this is a definition of primitive. Okay, I'll just quickly tell the statement again. If f belongs to R over a comma b and phi of x is from primitive. What is primitive? Phi of x is defined as an integral that is equals to integral f of x dx for all x belongs to ab. Our primitive is also known as antiderivative of f of x. Then we got to prove this. That is integral a to b f of x dx is equals to phi of b minus phi of a. I hope you all remember the note point. Just remember the note point and then we'll see whether we'll be using this in this theorem or not. Quickly moving on to the proof of the theorem. So first, what is that they gave? They gave it as Riemann integral. Write down that f belongs to R over a comma b. What is R over a comma b? This implies, as we are talking about the integration, integral a bar to b f of x dx is equals to integral a to b bar f of x dx is equals to integral a to b f of x dx. I hope you remember this statement because we have earlier proved in one of the theorems. Okay, this is what we'll get if it is Riemann integral. And now as it is Riemann integral, we will be defining partition P, that is a is equals to x naught, x1 and so on up to xn is equals to b, be a partition. Be a partition of what? Of closed interval a comma b. Okay, now as we spoke about partition, obviously subinterval and length will be coming into the picture. So again, given that IR, what is IR? The rth subinterval, that is xr minus 1 comma xr. Okay, after this, what is the next thing that you got to do? Obviously, if you have subinterval, you'll even have to find the length. So the length be delta r. Now we have took this, then we had partition, then we had subinterval, and then we had length of the partition. Now coming to the primitive case. Now I wanted to prove the primitive case. So what is that? Given that they gave, what is that they gave? Phi of x is primitive. So now we have to take this. So what is primitive for what? Phi of x is primitive of f of x for all x belongs to a comma b, right? For all x belongs to closed interval a comma b. Now, what is that? It is an antiderivative. So I'm just considering phi dash of x is equals to f of x for all x belongs to closed interval a comma b, right? And then as phi dash of x is equals to f of x, we can clearly tell that this phi is derivative or derivable, right? From the derivability condition. Phi is derivable on closed interval a comma b. Okay, let this be till here we just proved it is derivative, and we also know that every derivable is continuous, so we can tell phi is continuous on closed interval a comma b. As it is continuous on closed interval a comma b, it will also be continuous on the rth subinterval. So phi is continuous on xr minus 1 comma xr. As it is continuous on the whole interval, obviously it will be continuous on the rth subinterval, and as it is continuous, it will be derivable. So it is derivable where? On the same interval, derivable on xr minus 1 comma xr. Okay, now by what is as we have continuous and derivative, so I'm making use of Lagrange's mean value theorem, as we have earlier studied. Lagrange's mean value theorem. Okay, so what is Lagrange's mean value theorem? If f is continuous and f is derivable, you will be having the statement stating f dash of c is equals to f of b minus f of a by b minus a. So this is what the Lagrange statement says. So here what are a's and b's? xr minus 1 is a and xr is b. So I'll just write this in the next slide. That is, we are making use of Lagrange's mean value theorem. So there exists some epsilon 1r which belongs to the interval. What is that? xr minus 1 comma xr. I'm taking it as open interval because you know that derivability is just defined on the open intervals itself. Just make a correction in the previous slide. I think I've wrote closed, but make it as open. So phi dash of epsilon 1r is equals to phi of xr minus phi of xr minus 1 by same thing, xr minus 1. This is we took from Lagrange's. What is that? F dash of c is equals to f of b minus f of a by b minus a. Okay. Now this what is this? We have already know that phi dash of x is equals to f of x. So in place of phi dash of x, I'm just substituting this one. What is that? F of x. So you'll get f of epsilon 1r, and I'm multiplying this one with this. So you'll be getting xr minus 1. Okay, till here it is finished, and you'll have the numerator, that is phi of xr minus phi of xr minus 1. Okay, now in the next step, what is that we have to do? We have to add summation on both sides, that is multiply summation on both sides. So if you multiply summation, what is that you'll have? Summation r is equals to 1 to n f of epsilon 1r into xr minus 1 is equals to summation r equals to 1 to n phi of xr minus phi of xr minus 1. Okay, now what is that we have to actually prove? Integral f of x dx is equals to limit norm p tends to 0 and summation f of x dx. Okay, this is what we got to prove. So as we have as we already have summation, now we will be taking the limit, that is norm p. So as we have already multiplied with summation, we will be multiplying it with norm p on both sides. So limit norm p tends to 0, summation r equals to 1 to n f of epsilon 1r into delta r. So why are we writing delta r? Because I have already told you what is delta r? B minus a, right? Summation delta r is b minus a. So I'm just writing that one. Limit norm p tends to 0 and f of epsilon 1r into delta r. So this will be equals to limit norm p tends to 0. Summation r is equals to 1 to n. Same thing. Phi of xr minus phi of xr minus 1. Till here, I think you don't have any doubts till here. Now, moving on to the next step. But what is that we already know? We know that, but this limit norm p tends to 0, summation of f of epsilon 1r into delta r is clearly equals to integral a to b f of x dx. Okay, so this entire thing is integral a to b f of x dx. In place of this, you got to substitute this one. We'll just solve that in the next slide. So what is that you have? Integral, I'm just substituting it directly, integral a to b f of x dx. So integral a to b f of x dx is equals to, same thing, we got to write the whole thing. Norm p tends to 0, and there I'm just expanding the summation. So if you expand the summation, what is that you'll have? Phi of x1 minus phi of x0 plus phi of x2 minus phi of x1, right? And plus so on up to the last term will be phi of xn minus phi of xn minus 1. So here what are the terms that gets cancelled? Phi of x1, phi of x2, sorry, phi of x1, phi of x1 gets cancelled, phi of x2, phi of x2 gets cancelled, and here phi of xn minus 1 gets cancelled. So what is that you'll be having? Limit norm p tends to 0. There are only two terms left. What is that? This and this. So phi of xn minus phi of x, right? So what is phi of xn? And normally, like, you'll have a comma b. So this is x0 comma xn. So this will be equals to limit norm p tends to 0. This will be phi of b minus phi of a, right? So what is that we actually got? For this one, we have proved this. Therefore, what is that we can conclude? Integral a to b f of x dx is equals to limit p tends to 0, but there is no like norm p, there is no norm p term. So you can directly write phi of b minus phi of a. Hence, the fundamental theorem of integral calculus is proved. A very, very, very important theorem. Make sure that you add this in your important questions list. Now we will just look into one problem, one or two problems, how to solve when you apply fundamental theorem of calculus. So they are asking us evaluate integral 0 to 1 e power x dx using fundamental theorem of integral calculus. So how is that we will be solving? Let us take this is a, this is b. So what is a? A is equals to 0 and b is equals to 1. And what is f of x? F of x is equals to e power x, right? So what is that we know? We know that e power x is single real valued function. It is a single real valued function, right? A power x is a single real valued function where on closed interval a comma b. Next, f of x is equals to e power x is continuous. Obviously, when you draw the graph of e power x, you'll have a continuous graph. So continuous on closed interval a comma b. This implies if every continuous function is Riemann integral. So if f is continuous, f will be Riemann integral of a comma b. Okay. That is what is a comma b here? 0 comma 1. So in place of a comma b, you got to put this as 0 comma 1 and this as 0 comma 1. Right? Now, in the next step, we will let us define like the formula that we have. Phi of x is equals to primitive phi. What is that? If f is in a Riemann integral, then phi is primitive. If what is phi? That is integral f of x dx. Right? So substitute the values. That is, this implies phi of x is equals to what is f of x? Integral f of x is e power x into dx, and integral is from 0 to 1. So what is integral of e power x? E power x itself, and the integral is from 0 to 1. So you will be having e minus e power 0. So that is e minus 1. Okay, this is what we got for phi of x. And what is the exact formula? This is phi of when phi of x is primitive. So now we will be substituting in the formula of fundamental theorem of calculus. So what is that? Integral a to b f of x dx is equals to phi of b minus phi of a. Phi of b minus phi of a. So what is integral? Integral 0 to 1 e power x dx. That is equals to what is that we got? We got e minus 1. So this is what the fundamental theorem of calculus says by using a function. Okay, you may try it for integral 0 to pi sine x dx, and then integral 1 to 2 1 by x dx, and third one is integral 0 to 1 1 by 1 plus x into dx, and the fourth question is integral 1 to 2 x cube plus 1 into dx, and the fifth question is integral 0 to 1 1 by 1 plus x square into dx. So you may try for all these in the same way. First find phi of x, that is integral f of x dx, and then write the formula, that is integral a to b f of x dx is equals to phi of b minus phi of a. Then you will get the required solution for this. Now moving on to the next theorem, which says, the next theorem says, if f belongs to R over a comma b, then they are asking us to prove that integral a to b f of x dx is equals to limit n tends to infinity summation r is equals to 1 to n h into f of a plus r h. And what is h? H is equals to b minus a by n. So how will we prove this? First, write the given information. What is that they gave? They given that f belongs to r over a comma b. What is that? If f belongs to r over a comma b, and we are talking about the integral. So how is that we can write integral a bar to b f of x dx is equals to integral a to b bar f of x dx, that is equals to integral a to b f of x dx, right? Till here, what is that? We have the required information. Now, in same old story, you got to find the partition P, that is a equals to x naught, x1, and so on up to xn equals to b. Be the partition on closed interval a comma b. Then IR be the rth subinterval, that is xr minus 1 comma xr, and delta r be the length of the subinterval. All old stories. And here, 1 second. Instead of x naught, x1, x2, so on up to xn equals to b, we are talking about a plus rh. I hope I gave you the definition earlier, like there was a note point for partition when you have h. So what is that you'll be writing? The reason I've gave you all the partitions is because like the regular thing. But as we are talking about h here, we will be defining partition P is equals to a plus h, and so on up to a plus nh, right? This be the partition of a comma b, right? Where what is h? H equals to b minus a by n. Now, what will be IR? IR will be the rth subinterval, but we were talking about a plus h, a plus 2h and all. So IR will be equals to a plus r minus 1 into h, comma a plus rh. The reason why we are taking a plus r minus 1 into h and a plus rh is because we have defined partition in terms of h. But what is h over here? It is b minus a by n. Next, coming to the length. So what will be the length of the subinterval? The length will be delta r is equals to h. Okay. Now we will be defining the epsilon and this relation. So how is that? It will be let a into, or this one, we have to write this one first. A plus r minus 1 into h is less than or equals to epsilon 1 r, which is less than or equals to this one, a plus rh. So this will lie between a plus r minus 1 into h and a plus rh. Okay. Now integral a to b f of x dx, integral a to b f of x dx is equals to limit n tends to infinity summation r is equals to 1 to n h into f of a plus rh. Okay. See, this is epsilon 1r will lie between a plus r minus 1 into a plus rh. So that is the reason we will be getting this one, that is limit n tends to infinity summation h into f plus rh. Okay. Next, moving on to the next theorem, which says if f belongs to r over 0 comma 1, then prove that integral f of x dx is equals to limit n tends to infinity 1 by n into summation f of r by n. F of r by n, and the summation is for r equals to 1 to n. So we'll just quickly prove, as they gave it is f belongs to r over a comma b. What is that we can take? And 0 comma 1. So 0 bar to 1 f of x dx is equals to 0 to 1 bar f of x dx. This is equals to 0 to 1 f of x dx, right? As f belongs to r over a comma b. Next, as we have come with r over a comma b, now we will be defining the partitions only on this interval. So p is equals to, first thing will be 0, that is a, and then 1 by 2, and then you'll 1 by n, and 2 by n, and so on up to, it is from 0 to 1. So you'll have 0, 1 by 2, 2 by 2, and so on up to 1 but so you'll have n by n. Okay, n by n is 1. Let this be the partition on closed interval 0 comma 1. So what will be the rth subinterval? IR is equals to r minus 1 by n comma r by n. Like you have to just take the last terms. So what will be delta r? Delta r is equals to b minus a. So you'll be having 1 by n, right? So same thing. The epsilon 1r will be in this interval. So r minus 1 by n is less than or equals to epsilon 1r is less than or equals to r by n. And they already gave f belongs to r over 0 comma 1. So how is this defined? This is closed interval. Integral 0 to 1 f of x dx is equals to limit n tends to infinity summation f of epsilon 1r into 1 by n. So take epsilon 1r is equals to r by n. Okay, so now substitute, like take epsilon 1r is equals to r by n. So what is that you'll be having? You will be having integral 0 to 1 f of x dx is equals to limit n tends to infinity summation 1 by n into f of r by n. So how will you write this? This will be 0 to 1 f of x dx is equals to limit n tends to infinity. And as summation is with respect to r, so as this will be constant. So 1 by n summation f of r by n. This is what the required solution is. Now we'll quickly solve one problem. It is given as limit n tends to infinity. You may get these problems for short, r equals to 1 to n. Sometimes you may even get it for long. So n square into r square. So how will you prove? Or this can even be written as limit n tends to infinity. Limit n tends to infinity n by n square plus 1 square plus n by n square plus 2 square and so on up to 1 by 2n. Okay, now coming back to the solution, how will you prove this one? As they already gave limit n tends to infinity summation r equals to 1 to n square plus r square. Okay, so I'll just write the proof. So limit n tends to infinity summation r equals to 1 to n by, I'm taking n square common. What you'll have n square into 1 plus r by n whole square. So as and so this n gets cancelled and summation is with respective to n. So you'll have limit n tends to infinity, take that 1 by n out and then put summation r equals to 1 to n. So this will be 1 by 1 plus r by n whole square, right? So what is f of r by n now? F of r by n is equals to 1 by 1 plus r by n whole square, right? That is function in terms of r by n. So this implies what will be f of x? If f of r by n is r by n square, what will be f of x? F of x will be 1 plus x square, right? Now we know that f of x is continuous on closed interval a comma. As this is continuous, as this is continuous function, f belongs to r over a comma b. So in the same way, we got to write the definition. What is that? Limit n tends to infinity 1 by n summation f of r by n, that is equals to integral 0 to 1 f of x dx. Now we got to solve this one. So summation lies from r equals to 1 to n. I hope I'm clear till here. So we'll just define this further. So what is that you'll have? You'll have limit n tends to infinity, summation and r equals to 1 to n, f of n by, what is f of x? That is the given question, n by n square plus r square. So this is equals to, what is that in the right side? 0 to 1 f of x dx, right? 0 to 1 f of x dx. But we already know what is f of x. 0 to 1 f of x is 1 by 1 plus x square, because we wrote f of r by n in the form of 1 by 1 plus r by n. So f of x will be 1 by 1 plus x square. So what is 1 by 1 plus x square into dx? Tan inverse. Very good. So this will be tan inverse x. So the interval is from 0 to 1. So tan inverse 1 minus tan inverse 0. So what is that you'll have? This is equals to pi by 4. Okay. So whenever they ask you some question based on first limit n tends to infinity and then summation of some n by n plus 1 or something, you got to solve in this way. Okay. Let us quickly look into one more problem so that you'll have a clear idea. They just gave limit, prove that limit n tends to infinity 1 by n into e power 1 by n plus e power 2 by n and plus so on up to e is equals to e minus 1. So we'll quickly write down what is that they gave. They gave limit n tends to infinity and this one. So this will be equals to, I'm just writing it like this is the solution now. Solution. So this is equals to the formula. What is that? Limit n tends to infinity. This can be written as summation. 1 by n out. Summation r is equals to 1 to n e power r by n. Right? So what will that be? What is f of r by n? F of r by n is equals to e power r by n. Right? In the same way, what will f of x be? F of x is equals to e power x. So what is that we know? We know that this is continuous. What is that? F of x is continuous. Where f of x is continuous on closed interval 0, 1. If f of x is continuous, we know every continuous function is Riemann integrable. So f belongs to r over 0, 1. Now we will be proving the problem. Limit n tends to infinity 1 by n summation f of r by n. Right? And this is equals to 0 to 1 f of x dx. I hope I'm clear till here. Now we will solve the problem. So what is that? You have to write this one as it is. That is limit n tends to infinity 1 by n into e power 1 by 2, e power 1 by n plus e power 2 by n and plus so on up to e. So what is that? This one we have to write. Integral 0 to 1 f of x dx. What is f of x? E power x. E power x into dx. So what is integral e power x? E power x itself. And the interval is from 0 to 1. So this is equals to e power 1 minus e power 0. So something power 0 is 1. So e minus 1. This is what the required solution is. Okay. There are a few more problems. I just wanted you to try it by yourself. And thank you for watching this video.